In this video, we continue with Chapter 6, covering Section 6.4, all about transition matrices and similarity. Similarity is when two matrices are similar, a definition that we'll see in this video. Our learning objectives for this video are to find and use a matrix for a linear transformation relative to a basis, and to use properties of similar matrices and diagonal matrices. So in section 6.3, we saw that the matrix for a linear transformation mapping vector space V onto W depends on the choice of basis B1 for V and B2 for W. Oftentimes, we can find bases that give a very simple matrix for a given linear transformation. In this section, we will consider linear transformations T mapping V onto itself, and we will use the same basis for the domain as for the codomain. We will find matrices relative to different bases. In chapter 7, we will learn how to find the bases that give us simple matrices. So matrix for T mapping V onto itself relative to the basis B, where B is vectors V1 through Vn in that basis, is A, where we say T of X relative to B equals A multiplied by vector X relative to B. And then the matrix for T mapping V onto itself relative to this second basis that we're going to call B prime, with vectors V1 prime through Vn prime, has matrix A prime, where T of X with respect to B prime equals matrix A prime multiplied by vector X with respect to B prime. So then we can construct the transition matrix. Remember previously we saw transition matrices, we called them P. We're using the same notation here. So our transition matrix P that goes from B to B prime is represented by the columns that are V1 prime with respect to B, V2 prime with respect to B, through Vn prime with respect to B. So we are going to say that transition matrix P multiplied by X with respect to B prime is going to give us X with respect to B. And there's a helpful diagram down here. So the transition matrix from B to B prime is going to be the opposite, P inverse. So P inverse multiplied by X with respect to B is going to give us X with respect to B prime. So here's matrix P taking us from X with respect to B prime up to X with respect to B. And then on the other side of our diagram, here's matrix P inverse taking us from T of X with respect to B to T of X with respect to B prime. And then we see on the top of our diagram, matrix A takes us from X with respect to basis B to T of X with respect to basis B. And on the bottom of our diagram, matrix A prime takes us from X with respect to B prime to T of X with respect to B prime. So we see how we can construct some of these roots by multiplying the other matrices. So we're able to say that T of X with respect to B prime equals A prime multiplied by X with respect to B prime. And then we also have that T of X with respect to B prime equals P inverse, where P inverse, remember, takes us from B prime to B. From B to B prime, multiplied by matrix A, multiplied by matrix P, where matrix P takes us from B prime to B, all multiplied by X with respect to B prime. So you can see how that map works out here. If you take a look here, it's like we're going around in this direction. So we're able to say that A prime is going to equal P inverse multiplied by A multiplied by P. And so that's, if we go backwards here on the diagram, here's P inverse multiplied by A multiplied by P. All right, so let's take a look at an example. This will help solidify our concept here. We're going to let T map R3 to R3, because remember, T maps the vector space back onto itself. And so we're going to use the standard matrix here that's given. And then we want to find matrix A prime for T relative to the basis B prime equals 1, -1, 1 for the first entry, 2, 1, 0 for the second entry, and -2, 0, 1 for the third entry. So we are going to take these entries and correspond them to the columns of our transition matrix. So the 1, -1, 1 here corresponds with the first column. And then we can take 2, 1, 0, transpose it corresponding with the second column. And our third column will correspond with the third entry, -2, 0, 1. So we use it to calculate A prime. So A prime is going to be P inverse multiplied by matrix A multiplied by matrix P. And we end up with this diagonal matrix with the 2's on the second and third diagonals and a 0 on that first diagonal entry. And so this kind of multiplication, the P inverse A multiplied by P, outsource that to SIMPy or other technology. You don't have to do that one by hand. And you can go into SIMPy to verify these calculations if you put in matrix A, put in matrix P once you construct them, and then do the multiplication in SIMPy or other online technology or graphing calculator. All right, in this next example, we're gonna do a similar calculation, but with different bases. So we're gonna let B be this bases 1, 3, and -2, 2 in R2. And then B prime is gonna be another bases in R2. This will be -12, 0 and -4, 4. And then A is going to be this matrix here, 3, 2, 0, 4, a 2 by 2 matrix. And that's the matrix for linear transformation T, and it maps from R2 to R2. It's a square matrix, we see that. And then following our notation from the diagram on the previous slide, A is a matrix relative to B. So we want to find 4 things here. We're going to find the transition matrix P from B prime to B. We're going to use the matrices P and A to find vector V with respect to B and T of V with respect to B, where V with respect to B prime is given to us, that's -1, 2. Then we're going to find P inverse and A prime. A prime is that matrix for T relative to B prime. And then we want to find T of V relative to B prime, and we'll show that in 2 different ways. So let's take a look at these results. All right, so our first task here in part A is to find the transition matrix P from B prime to B. So we do that in the same way that we found the transition matrix C earlier in the semester. So we take B and adjoin it with B prime. So that's 2 by 2 matrices here, and those come from just the rows of each bases corresponding with the columns. So these are the 2 rows from B, and then these are the 2 vectors from B prime that are now here in columns. And then we row reduce, so we end up with the identity matrix and the matrix P. So right here is our matrix P, the 2 by 2 matrix, 6, 4, and 9, 4. So that part should be familiar, earlier sections in our textbook. Part B now, we're going to use these matrices P and A to find vector V with respect to B and T of V with respect to B, where we're given that V with respect to B prime is -1, 2. So here's our V with respect to B prime right here that was given to us. And then we are calculating P multiplied by that. And so we get our resulting vector over here, the coordinate matrix for V relative to B. So this over here is V relative to basis B, because we use our transition matrix to get there. And then furthermore, we can say that the image of V under T relative to B is matrix A multiplied by V of B. So we get our T of V relative to B through that calculation, and that is the vector for -4. All right, part C asks us to find P inverse and A prime. So P inverse we can find using the formula for the inverse of a 2 by 2 matrix, or you can put it in SIMPy. and verify our results here. Remember, it's 1 over the determinant, and then you flip the negatives on the diagonal there. And so the matrix T relative to B prime is then going to be calculated using our formula, A prime equals P inverse AP. And so you just plug in our matrices here and let Simpy or other technology do the rest, although these are 2 by 2, so you could probably crank out the calculations by hand about as fast as you could type them into Simpy. And then you can verify here that we get matrix A prime, which is 0, -4/3, and 9, 7 in the second row. This is a 2 by 2 matrix, which is just what we were expecting. So our last calculation is to find T of V with respect to B prime, and we're asked to do it in 2 ways. So the first way you could do is multiply P inverse by T of V with respect to B, and you get the resulting vector -8/3, 5. And so we say this is the image of V under T relative to B prime. And that was the calculation we did right here, P inverse multiplied by T of V relative to B that we found up in part B. This came from here. The other way you could calculate is you could also find the image of V under T relative to B prime by multiplying matrix A prime by V with respect to B prime, and you get the same result. So if you think back to that diagram we worked from, it's like going in 2 different directions around the diagram. So 2 different calculations, 2 different routes to get the same value, the same T of V with respect to B prime. Okay, let's talk about similar matrices. So similar matrices are when you have 2 square matrices that are related by this equation here. So we say A and A prime are similar if A prime equals P inverse A multiplied by P. And let's go ahead and put this in the next video because I don't want to run too long in this video. So our next video will cover the similar matrices.